Welcome to Future Talk. On today's program, we're going to talk about the search for Earth-like planets in other solar systems and why that search is important. I have two guests from NASA's Ames Research Center, which is one of the world's top space research facilities. Pete Worden has been the director of the Ames Research Center since 2006. He's a retired brigadier general in the U.S. Air Force with a Ph.D. in astronomy, and he's considered an expert in almost every area of space research, both civilian and military. He's deeply involved with the Kepler Mission, which has already identified numerous planets circling other stars, some of which appear to be in the so-called Habitable Zone. Marcelin Belicoff is an astrophysicist at Ames, where he's working on the next generation of experiments designed to do direct observations on newly found planets to see if they might actually be capable of supporting life. Gentlemen, welcome to the program. Pete, let me start with you. Why is this research important to the tune of many hundreds of millions of dollars? What do we gain by looking for Earth-like planets?
NASA is funded, of course, by the public, and we do three main things. First, we make life better here on Earth, and our oldest mission is aeronautics, so that's one of the things we do. Second, really starting in the 60s, we are sending humans to space, and we think this is the next step towards human expansion into the solar system and maybe beyond. Finally, and to me, the most interesting, is we do science. And in science, to many people's minds, and I think probably just about everybody I talk to, there's three fundamental questions. How did the universe begin? How did life begin? And the third question is, where else is it in the universe? The last two questions are called the astrobiology questions, and those, I think, are of great interest to people everywhere, and we're making progress on those.
Now, let's say we discover planets that might support life. What do we do with that information? The planets are so far away, it seems unlikely we'll ever be able to visit them.
Well, not necessarily. Perhaps centuries in the future, but more important, it really tells us about who we are. You know, what's the meaning of our life? It's been a question that for thousands of years people have asked, and answering that question, or at least beginning to answer it, is really important to everybody.
So if we discover life on other planets, does that increase our estimation of ourselves or lower it? Are we less special?
I think it increases it. The idea that you're not alone is a really comforting one, and I think it's something that people would like. People will help make us think better of our own future.
Is there any reason to think that there wouldn't be life on other planets?
Well, there's no reason right now to think either way. We only know of one planet in the whole universe that has life, and our key job is to answer that question: is there life elsewhere? Starting in our solar system, but looking at other solar systems as well.
Well, one of the main ways that we look at other solar systems is through the Kepler mission, and we're going to talk about that. But before we do, we have a video put together by NASA which shows some aspects of it. And this video has no voice track on it, so Russ, I think you're going to give us a little live narration about it. So can we go ahead and run that video, please?
5, 4, 3, 2, engine start, 1, 0, and liftoff of the Delta II rocket with Kepler.
What you're seeing here is the Kepler launch on March 9th, 2009, I believe. And that's Kepler in space. You can see it's in a solar orbit, a similar orbit that Earth is in, but it's moving slightly faster than the Earth.
So it's always about the same distance from the Earth?
Actually, it's moving further and further away from the Earth, and eventually it will catch up with Earth. What you see here is how Kepler works. So Kepler is looking at a lot of stars, and what it's detecting is the brightness of the stars, and it's looking for little dips in the brightness caused by planets crossing the face of the star. So if a planet happens to cross the face, Kepler is not resolving the actual star or the planet, but it is capable of detecting little dimmings of the star. And this chart shows where Kepler is looking. So the little yellow boxes are showing Kepler's field of view. This is showing Kepler 10b. It's a star system with the first confirmed rocky planet by Kepler, This planet is somewhat bigger than the Earth.
This is something Kepler actually found, but this is obviously an animation.
Yes, absolutely. And this planet is far too hot to be habitable. It's way too close to a star, but it's significant because it's the first rocky planet that Kepler found. This is showing Kepler 16, the Kepler 16 system. And the cool thing about this system is that it's the first one where a planet has been found that's orbiting multiple stars, 2 stars. It's called a circumbinary system. And this one here, I believe, is Kepler 62, which has just been announced a month or so ago. And these are the first planets, along with Kepler 69, that are rocky and in the habitable zone. So these are the first potentially habitable confirmed planets that have been found by Kepler. And you can see their orbits right now, and highlighted in green is the habitable zone around the star, where the temperatures of planets inside that zone are such that liquid water can exist.
So do you say that the Kepler mission has met or exceeded its expectations?
It's a spectacular success. We had planned on something like 3.5 to 4 years. We've met that, and we're finding planets everywhere. In fact, we now believe that there may be planets around essentially every star in the galaxy.
Now, how does that happen? I've heard one theory where the solar system starts out as a ball of gas, and then as it spins around, it condenses, and the planets are formed at the same time out of the same material, as opposed to just flying in from someplace else. Is that the prevalent theory still?
Yeah, absolutely. So the gas starts out as this big nebulous kind of thing, and then it compresses because it self-gravitates, so it attracts itself, and as it attracts itself and becomes smaller, the little bit of spinning that it has gets faster, just like a figure skater spins faster as they fold their arms. So, and it spins up, and as it spins up, it flattens itself into a pancake, just like a pizza would flatten into a flat disk. So, and then inside that disk, you have clumps of gas and little particles forming into rocks, and planets form.
How many stars is Kepler able to keep its eye on at any given time?
It's about 150,000 that we look at simultaneously.
Because if a planet passes in front of it, if the planet is the same distance as the Earth is from the Sun, it would seem that you'd have to wait a year before you saw it pass by again to establish a pattern.
Precisely, and that's why this mission was designed to last at least 3.5 or 4 years, so we would see several passages. Now, also, of course, the solar system or the stellar system has to be oriented edge on so that the planet will pass in front. So with something like the Earth, there may only be 1% of solar systems that are aligned so that we could actually see an Earth-size planet in an Earth-like orbit pass in front of the star.
You're not really seeing the planet itself, you're just seeing the star dim a little bit, and you're assuming that that's because a planet is passing in front of it.
Yep. We're inferring the presence of a planet.
Now, speaking of the Kepler mission, we just happen to have a scale model of the thing right here. Pete, maybe you could explain a little bit some of the parts of this. And well, how big is this thing in reality?
This is about 20 feet tall, so put on the end, it's the size of maybe a car, a big car.
Okay.
The key piece to it is the telescope. This is a telescope that's about 1 meter in diameter, and that's this central part of it here. This are the solar panels, so it provides the power for the telescope. And then that's all attached to what we call a spacecraft bus, which is this bottom piece. That does all of the managing things. It has a antenna here that about every 2 or 3 months we point it at the Earth and get the data down. It's got data.
Just every 2 or 3 months?
Well, that was actually a cost-saving move when we built it. Originally, we wanted to have an antenna we could keep permanently pointed at the Earth, but to save the taxpayers money, we found a D-scope, it's called, and so we have to actually turn the antenna towards the Earth. It also has thrusters, rockets, that enable us to orient the rough pointing. And then for fine pointing, there are these reaction wheels. There are 4 of them I have to tell you, 2 of them have failed. So we are in kind of a standby mode right now where we're seeing if we could restart them or fix it. But the good news is that we've completed our baseline mission, and we're going to try to see if we can milk a little more out of it.
Now, how does it keep pointing in the same direction if it's constantly rotating around the sun? Is it aiming perpendicular to its orbit?
It's aimed at a particular part in space, which is on the opposite, or 90 degrees, or roughly 90 degrees to the sun, so we never get in the way of the sun. But what we have to do is, as we go around the sun, the satellite is also going around the sun. So once every quarter year, we turn it. And so that's one reason we have these thrusters. So you're pointing at it, and you've orbited enough, so you have to turn it again to keep everything oriented right, and we turn it 4 times during the year. So it's a fairly complicated dance with the stars that we're doing.
What would you say was the most difficult thing of building this?
Inside this telescope is the sensor array. This has like 1 million by 1 million CCD elements. These are the same kind of things you have in your camera. This is the largest digital camera we ever put in space, and that was really hard to get that to work right. We have to measure the light within about 10 to 20 parts per million. So to get the accuracy, that took quite a while. That was a real challenge for us, but we did it in the end, and this is a spectacular machine.
And I understand that NASA also has projects beyond the Kepler mission, and we're going to talk about those. But first, Rus, I believe you brought a slideshow along, and you're going to show us a few slides to illustrate some of the stuff that Ames is doing. So let's go ahead and bring that up. Could we see the first slide, please?
Okay, so this slide shows that the questions of other worlds, other Earths, is a really ancient one. And all the questions that Pete talked about in the beginning, are we alone, are there other Earths out there, is at least 2,000 years old. So this is a quote from a Greek philosopher, Epicurus, who basically stated that there can be worlds like our Earth elsewhere in the universe. And this is amazing that in all the time between Epicurus and our age, 100 generations, we are in the generation, we're privileged to be in the generation that's answering this age-old question. So I think this is amazing.
And here's another slide. So what's this showing us?
So this is showing the fact that habitability depends on planet size. If a planet is too large, it retains too much of the primordial hydrogen gas and swells up into a gas giant like Jupiter, which is uninhabitable as far as we know it, or at least not habitable by life as we know it. And then if a planet is too small, like Mars, or smaller than Mars, then it doesn't have enough gravity to retain an oxygen atmosphere, again rendering it incapable of supporting life as we know it. So there's about a slop of a factor of 2 around Earth size where a planet is considered habitable. And we call planets larger than Earth super-Earths that are between 1 Earth size and 2 Earth size super-Earths, and they're still habitable. And roughly when a planet gets more than 2 Earth size, we think it's no longer habitable. So,
okay, and there's another slide.
Another factor that determines habitability is how far the planet is from its star. If it's too close, then all the water evaporates. If it's too far, all the water freezes. So there's a region around the star called the Habitable Zone where habitable planets can exist. So Kepler finds what are called potentially habitable planets. Well, actually, it finds many planets, but one of its mission focus is to find habitable planets, or potentially habitable planets, which is defined by being roughly Earth size and inside the habitable zone. And one of the cool things that Kepler has discovered thus far is that about 15% of stars, or at least 15% of small stars, have potentially habitable planets in our galaxy alone. What that means is that basically for every human alive on Earth today, there is a habitable planet, or at least one habitable planet. So you can have a habitable planet.
I can have my own planet.
Yep.
Stake my claim now.
Your friendly neighborhood baker can have a habitable planet. You know, a little girl in China can have a habitable planet, all to themselves. This is just amazing.
These are candidates. These are planets that have not been ruled out. as being able to support life?
Well, Kepler is determines the frequency of planets. So it didn't actually find 8 billion habitable planets, but it has determined that if if the statistics of all the stars are similar to what it has found, then in our galaxy there are more than 8 billion potentially habitable worlds.
And it took a good statistical sample.
Yes, exactly.
That we can extrapolate from.
That's exactly what it's doing. So, in that sense, Kepler has been a wildly successful mission.
Okay, now here's another slide. This looks like a spectrograph.
So as cool as Kepler has been, one thing that it cannot do is it cannot determine whether a planet is actually habitable. It can determine that it's potentially habitable, but it cannot distinguish between a hellhole like Venus, whose surface is hotter than the inside of your oven, and a paradise like the Earth. In order to differentiate between them, we have to figure out what's inside their atmosphere. And the way we do that is by doing something called spectroscopy, which is spreading out light from a planet into its spectrum, like a prism does, and then seeing patterns in that spectrum of frequencies of light that have been absorbed by different gases, like carbon dioxide and oxygen and water.
So that means that you can aim your optical instruments at such a fine angle that it can pick out one tiny little planet, hundreds or thousands of light years away? So interference?
Yes, there are several ways of doing that. You can do it with transits, because with transits you observe starlight passing through the planet's atmosphere. But this is very difficult to do, and maybe even impossible to do for small planets like the Earth. But if you can directly image planets, take a picture of a planet, then spectroscopy becomes easier, and then you can take its spectrum and figure out if there's water, oxygen on the planet, and whether it's habitable. And in particular, one thing that's very important to look for is oxygen. Oxygen is a biomarker, which is a fancy way of saying it's an indicator of life, because oxygen, at least as we know it, can't easily exist without life. On Earth, if life were to suddenly disappear, all the oxygen in the atmosphere will disappear in about 1 million years, which is a blink of an eye on geological timescales. So if we find oxygen on an Earth-like planet, we would be hard-pressed to explain it any other way than life. So.
Okay, let's look at the next slide.
So I mentioned that in order to take a spectrum, it's kind of difficult to do it with transits on small planets. So what I'm working on, and a lot of my colleagues, is on trying to directly image a planet, which means taking a picture of it. The main challenge there is that the brightness of a star is many, many times greater than the brightness of a planet. Our sun, for example, when viewed from far away, is 10 billion times brighter than our Earth. This is similar to the brightness difference between a firefly and a searchlight.
I understand that in the previous slide, the firefly was there, but you couldn't see it. Now that the searchlight is off, you can see the firefly.
Yep, absolutely. So the challenge there is to be able to pick out a little firefly circling around a searchlight. And not only that, but to do it from 10 or 100 miles away, because stars are so far away that the angle between the star and the planet is very, very small.
And there it is, the firefly itself.
Yep. So this is a very challenging problem, but technology has been maturing, and we're essentially capable of demonstrating this type of performance in the lab.
Okay, and I think you've got one more slide.
Yep. So this is a time scale of NASA missions which have to do with exoplanets. There's Kepler, of course, and then the next exoplanet mission after Kepler is something called TESS. It stands for Transiting Exoplanet Survey Satellite. And it's a small mission, even smaller than Kepler, and it's a transiting mission, which means it looks for dimmings of the star rather than directly imaging the star, just like Kepler does. And the main difference between TESS and Kepler is that TESS will be looking at nearby stars and all over the sky, whereas Kepler was focusing its gaze onto a single field of view. TESS won't be able to get to quite the planets as small as Kepler was able to, but it would be able to look all over the sky. The next one after TESS is the James Webb Space Telescope. It's usually considered to be the successor to Hubble. It's a big general-purpose telescope that does many more things than exoplanets, basically does everything. But it can do things related to exoplanets also, like transits, and it also has can also do limited direct imaging as well.
Does the success of each mission determine what you do for the next mission? So you take your results and decide what to do next?
In some respects, it's more the science that drives the missions and what the state of the science at a given time. And then looking towards the future, in my opinion, the domain of direct imaging missions. So EFTA is also going to be a multi-purpose telescope, but putting a direct imaging instrument is under consideration for it, and it won't quite be able to get down to Earth's, but it would be able to get to larger planets, and maybe if we're lucky, it could bag a few Earth-sized planets.
Maybe I could add something about
Yes.
AFTA. This is an example of economy in the U.S. government. These were leftover telescopes built by the national security community. They were used to look the other way, to look down, and they have donated 2 of them to NASA. So we might be able to save a lot of money. The taxpayers already built them, and we use them for astrophysics.
So that raises an interesting question. Does NASA try to be ingenious with the use of funds? Because obviously space research is very expensive. Is it always looking for cost-cutting methods?
Oh, absolutely. James Webb Space Telescope, for example, we've teamed with the European Space Agency. So they're doing the launch vehicle and some of the instruments. So international cooperation is one way. New technology is the other. That's what Rus has been working on, is technology so that you can do things you couldn't imagine a decade ago a lot more affordably. Yep.
Well, you're mostly trying to work on narrowly defined missions, or are you trying to build a broad platform that can support a whole array of projects?
Well, we do both. The way NASA does decision-making in science missions is every 10 years, the National Research Council brings together all of the scientists in a particular discipline and comes up with what they call a decadal survey. And this survey is the consensus of our scientific community of what can we do, what do we need to do, and what's feasible in the next decade. Then, of course, NASA tries to translate that into real instruments. Now, sometimes we get cost overruns and things get pushed out. Other times we find a new technology or a new way to do it, and we can do things faster.
Well, who decides what NASA works on? Who decides what projects will get a green light and which ones won't? Does Congress decide? Is it the president, or is it internal, like NASA proposes, subject to Congress opening the purse strings?
Well, as a U.S. government agency, of course, we have many bosses. Ultimately, it's the taxpayers. But the scientists give us the list of what they want done. Then we translate those into proposals. We submit those to the White House, to the Office of Management and Budget in the Science Advisor's Office, and they then will maybe readjust those or readjust the balance between astrophysics and earth science, for example. And then that's submitted to Congress, where the congressional committees go through, and we get a lot of help from our 550 or so board of directors, and then we get an appropriation and move forward. But it's a lot of interaction, and it's really a very exciting process, and I think it works pretty well.
Yeah. Is there a general consensus? In the early days of the space program, it was really popular, and we were competing with the Russians. Nowadays, is it still easy to get funding? Is there still a lot of support for space research?
It's never easy to get funding. We have to make a very good case that we're going to do these things affordably, and that they are the key science questions if it's a science mission, and that this science area is what the public and the Congress is interested in. On the other hand, NASA has very broad support. Our budget it may seem like a lot of money. It's a little over $16 billion, but it's a few tenths of a percent of the federal budget. So we're not we're not one of the really big areas, but the support of it is very, very broad. We find that we do surveys, the public says, look, NASA's a good thing.
Now, what's the biggest need in space research? Is it the propulsion systems themselves, the ability to get stuff out there faster and more dependably, or is it more the optics, the instrumentation?
Well, for this problem, the exoplanets, and Rus has a lot of expertise on that, it's really the optics.
And I guess the question of propulsion versus telescopes is an interesting one, because particularly here, because we cannot with foreseeable technology actually go to these planets. However, we can go there remotely, if you will, with telescopes and survey those systems remotely. And actually, our remote sensing in this sense has surpassed the technology of Star Trek, because in Star Trek you actually had to go to a planet system in order to be able to determine what planets are in that system. And we, with obsolete 21st century technology, can already do that, even though we cannot come close to Star Trek's propulsion of actually going there.
Now, speaking of optics, you've got a little optical device on the table. We just have a couple of minutes left, but maybe you could just give a very quick demonstration of that device.
Absolutely. So these are some of the optics that I use in my lab and my group use in the lab to test how well we can block a star. So to block a star, we use instruments called coronagraphs, and these are components of a coronagraph.
We only have 1 minute left, so you'll have to...
So one key component is masks that block the star, and this is the kind of mask. And another type of component is optics that modulate the light in some way, like this lens here. So you can see it's not a typical lens, it's kind of a fancy lens that does weird things to my eye.
So you can create your own little eclipses by... This will actually block out the stars so the planet is more visible?
That's right. This can create an internal eclipse inside the telescope.
I'd love to ask more questions, but unfortunately we are out of time, and I'm sorry about that. I'd like to thank both of you for being here today. Pete Worden, Director of NASA's Ames Research Center, Marcelin Belicoff, astrophysicist at Ames. Thank you for watching. Visit our website, www.futuretalk.net. For Future Talk, I'm Marty Wasserman. We'll see you next time.